right, so if you haven't already, so a couple of you already sent me a text. Go ahead and send a text to this number for attendance purposes. Make sure you write logic control in the body of your text. So go ahead and do that now if you haven't already done so. The quiz. Now normally we'll have a quiz on every Friday at the beginning of class. Lasts about 12 minutes. What I decided to do today though is I'm going to give you a link to a video over the weekend on relays. I think I discussed this the other day. I want you to look at that video. The person in the video does an excellent job explaining relays, what they are, how they work. So what I'm going to do is the assignment is going to be you watch that video, and then I'm going to open up the quiz over the weekend. So you have Saturday, Sunday. You'll just write up a few things that you learned from the video. It'll be pretty simple. But make sure you watch the video, and then when you click on the quiz, it will be timed. So make sure you've watched the video, maybe take a few notes, and I don't see any issues with the quiz. It'll be pretty straightforward. So this quiz this week will be a little different. You'll have the weekend to do it, but starting next week, you'll have a quiz at the beginning of class. It'll last about 12 minutes, and as I said, it'll be timed. So go ahead and send me the text, the quiz. Monday, I don't know if Monday is an official holiday, but Monday we will not meet for class. It's Martin Luther King Day. And then the last thing is, if you missed the last class, make sure you go to the home page. At the bottom of the list of topics, there's a link that says past videos. Make sure you click on that link, and at some point in the near future, go back and review the last class if you missed the last class. Before I get started, does anybody have any questions for me? Any questions over what we talked about last time, or just general questions? Okay, well, let me go ahead and start. I want to start by just briefly reviewing what we talked about, some of the major topics we talked about in the last class. One important thing we talked about was types of signals. And remember, in this class, a signal is either a voltage or current. Doesn't really matter how you think about it. It's a voltage or current. What's going to end up happening is that those signals are going to store or transfer information from us in the form of what we call digital. So we talked about signals, and there are two types of signals. There are analog signals or analog quantities. There are digital signals or digital quantities. Now, we define the term analog. An analog signal is one that's continuous. A digital signal is one that's discrete or broken up. We represent digital by using pieces or one value or another value. Now, what we like to do with these signals is represent something in the physical world. And it turns out that most, not all, but most of the quantities we measure in the physical world are analog in nature. For example, time is continuous. That's analog. If you measure pressure applied to an object and the pressure increases, that's continuous. Most of the physical quantities that we want to measure are physical if they're a natural quantity. So basically what we want to do, if we want to measure those devices, we want to measure those quantities, and we want to use that information in any kind of a computer. Now let me back up. What's a computer? Remember we said that the computer is any device that contains a microprocessor. So it's true that your laptop contains a microprocessor. That's a computer. It's true that your desktop contains a microprocessor. That's a computer. But it's also true that your cell phone has a microprocessor in it. Your cell phone is really a computer. If you have any kind of programmable digital device like a microwave or refrigerator, those are really computers. And so any device that contains a microprocessor, I'm calling it a computer, the only thing that device understands is zeros and ones, basically digital. So if I want to get information into the digital device, if the information is analog, I got to first take that analog and I got to do some things to it. I got to represent it in a digital way, and so that we can put that into the microprocessor, and then we can manipulate that data. And we went through how you would do that in the last class. And so we talked about digitizing, the fact that you take an analog signal, and then we sample points on the signal, and then we represent each one of those points with a series of zeros or ones. And that's what we mean by digitizing. So ultimately, we ended up talking about something called the digital advantage. What advantage does digital have over analog? Well, there's several, but the main two I wanted to get across to you is that, number one, digital information can be copied over and over and over again, and it doesn't lose any quality. So if I make a digital copy, in theory, the digital copy, I can make 100 copies from an original or a master, and that 100th or 1,000,000th or 1,000,000th copy is, for all practical purposes, exactly like the original. So part of the digital advantage is I can make as many copies as I want, and those copies will not degrade. The second important feature of the digital advantage is that I can take digital information and I can compress it. I can take a lot of information and put it in a very, very small space. So that turns out to be pretty important. All digital data is stored as zeros or ones. Now, a 0 or 1 is called a binary digit. A 0 or 1, we'll talk about binary, I believe that's next week or the week after. We'll go into detail of binary. But basically, a 0 or 1 is called a binary digit, and that system of zeros and ones is called a binary number system or binary system. And what they do is they take the B from the word binary and the IT from the word digit, take the B from binary and the IT from the word digit, and they make something called a bit. So we refer to a 0 or 1 as a bit. So we say computers or digital devices store bits. Now, I want to talk about, we kind of got into this a little bit in the last class, what really, because we know that digital devices, computers, cell phones, all those devices, really, they only understand current or voltage. You apply voltage, it takes in the current. So what really is a 0 or what really is a 1 inside of a digital device? I want to talk about that. Does anybody have any questions or comments over my brief review? This is kind of what we talked about in the last class, and this is kind of setting us up for what I want to talk about today. Any questions, anything I need to go over briefly before we get into what I want to talk about today? All right. Well, if there are no questions, I have some questions over here. I'm going to attempt to answer in the about 50 minutes I have left. How are zeros and ones stored in a digital device? I'm going to talk about digital pulses, and we'll talk about two types of pulses, ideal pulses and non-ideal pulses. Pulses are important because once we store the information, then we want to move the information around, and we do that using digital pulses. And then we'll talk about digital waveforms. There's two types, periodic versus non-periodic waveforms. Again, that's important for moving digital information around. And then along with this, there's these concepts of frequency period and something called bit time. We'll talk about that. What is bit time and how does that apply to the topic of interest? And then the last thing we'll talk about is data transfer, and hopefully we'll have enough time to do a quick calculation, a quick example, and if not, we'll do that on Wednesday when we meet. So let's talk about how are zeros and ones stored in a computer. Well, as I said before, the only thing devices can understand, an electrical device, is this idea of a voltage or current. And so what we'll do is we'll just focus on this, voltage. I can use voltage to represent digital information. And so the way it's done is we have voltage levels that are what we call two states. There'll be a one state or another. So what I want to do is represent a binary 1 or a binary 0. And the way I do that is I use a voltage of a certain amplitude to represent a 1. I use a voltage of a different amplitude to represent a 0. So these are binary numbers here, binary number 1 and binary number 0. The actual amplitude of voltage you use is arbitrary. It doesn't matter. You can use whatever you want as long as there are two different voltages. Typically what we do, we use these standard values of 5 volts and 0 volts. We use a standard value of 5 volts to represent a binary 1 and a voltage of 0 volts to represent a binary 0. And this diagram, these are what I call ideal levels. These are ideal. And I'll talk about that in a second. So here's what I'm saying. Let's say you want to store, remember the graph that we talked about in the last class? I think I had a graph, and I had something like time over here, I believe in hours, and I think this was temperature. And I said you're going to measure the temperature, you're going to record the temperature maybe every hour. And so the temperature might start out like, this was like degrees Fahrenheit. The temperature might start out maybe down here, and as time goes on, it goes up, maybe stays up, and then drops off like that. So here's a analog quantity that we want to digitize. So what does it mean to digitize it? Well, what we said was what we'll do is we'll take data points at these regular intervals. So I might take a data point here. There's a point right here. There's a point right here. So I sample these points right here. And then what I want to do to change this analog waveform to digital information is each one of these points I have to represent using 1s and 0s. So I might give this point that value, and this point will have another series of 1s and 0s to represent it. But when you do that, this is called a digital code. So right now what that is, if I write that down so you can see it, that code is it's a 1, 1, 0, 1, 1. So as a human, this is what we like to think about, these zeros and ones. But the question I'm trying to answer is, what really is a 0 inside the machine? What really is a 1 inside the digital machine? And what I'm saying is that these devices only understand voltages. So where you have a 1, 1, 0, 1, 1, what's really stored inside of your cell phone, your computer, your programmable device, what's really stored is, here I'd have 5 volts stored. Here I'd have 5 volts stored. Here I'd have 0 volts stored. Here I'd have 5 volts stored. And here I would have 5 volts stored. So I would have these devices, or these places inside of your digital device that actually holds a voltage of one value or another value. So physically, what a 0 or 1 is the presence of an amplitude of a voltage. In this case, 5 volts represents a 1, 0 volts represents a binary 0. And another term you want to be familiar with is we call that 5 volts or that 1 a high, and we call the 0 volts or binary 0 a low. So on a machine level, we're dealing with voltages and currents. Now what we like to do is abstract from that. We don't like to think about voltages and currents. So we'll never again think about it in terms of voltages. You just kind of got to know what's going on under the hood. We'll always refer to it using this, what we called it before, machine language. Machines only understand voltages or currents. Well, the machine language, when we abstract from those voltages, we call machine language basically is the binary system that we use to code information or binary numbers. This diagram here represents an ideal situation. In reality, you don't have exactly 5 volts representing a 1 or exactly 5 volts, 0 volts representing a binary 0. This is an ideal representation. In reality, what you have, I'm going to redraw this diagram up. This is the perfect or ideal diagram. Really what you have is this, and I do have a diagram on Canvas that you can print out, but really what you have is, to represent a binary 0, there's really a range. So I might have a range. Remember, this is my the voltage amplitude. So instead of having a voltage of 0 volts represent a 0, and a voltage of exactly 5 volts represent a 1, what I actually have is this range right here of voltage. And then I have another range more like this. So what I'm saying here is, instead of having, like right here, exactly 5 volts, you actually have this range here and here. And I don't know, there's a diagram that I have on Canvas you can look at. I don't know what the numbers are exactly, but let's just say that maybe the high value here is 5 volts, and the low value here might be 4.5 volts. And so then the value here might be, the low value might be 0 volts, and then the high value here might be 0.8 volts. And as I said, these numbers are they really don't matter. They're not exact values, so whatever you see on the diagram is what it is. The point is this, though. Instead of having exactly 5 volts represent the binary 1, or exactly 0 volts represent the binary 0, you actually have this range. For my example here, anything between 4.5 volts and 5 volts will be interpreted by the device as a 1. Anything between 0 volts and 0.8 volts will be interpreted by the digital device as a 0. And so in the real world, we like to think of it like this, and this is the way we'll think of it. We'll deal with the ideal, but just realize in reality, we deal with these ranges. Now, you might, or you should be thinking about something. You want to ask me a question. The question you should be thinking about asking is, okay, Samuel, can I get this? I get what you're saying. I deal with these ranges. And so I have a low range and a high range. What happens if the information falls in between those two ranges? What happens if my voltage amplitude is not between 0 and 0.8, or for this example, 4.5 and 5? What happens if it's like right here, maybe at 3? What will happen? And the answer is, this is called the forbidden zone. This is called the forbidden zone. You're not allowed to have a voltage, whatever the maximum low voltage is, to represent a 0, or the minimum high voltage is to represent a 1. Whatever those limits are, you're not allowed to have a value of voltage between those two. This is called the forbidden zone. You might say, okay, well, I get it. We're not allowed to have it, but what happens if we do have it? Well, the answer is, and your results will be unpredictable. And what I mean is, if you land in here between these two limits, you don't know if you're dealing with a 0 or 1. And so there's circuitry inside your cell phone or computer or digital device that prevents that from happening. So we always will land within the range, the max and minimum range for a binary 0, and the max and minimum range for binary 1. So again, we'll abstract from the voltage thinking. We know that these digital devices, what they understand is voltage and current. We'll abstract from that, and we'll only deal with the 0s or 1s. And we understand this, but we'll focus on this one. We'll deal with the ideal values in this class. Okay, so any questions over how 0s and 1s are stored inside of a digital device? Any questions? And I want to be clear, because this stuff is really pretty interesting. If you think about it, what I said was anything that contains a microprocessor is a computer. Anything. So your cell phone is a computer. With your cell phone, think about what kind of information you can store or transfer or transmit using your cell phone. You can speak into your cell phone. You can take a picture with your cell phone. You can make a video with your cell phone. You can do a whole bunch of different things, play games with but all of those, it doesn't matter if it's a picture, if it doesn't matter if it's a video, it doesn't matter if it's voice. If you look inside of if you can actually look inside of the machine, you can open up the hood and see what's going on in the microprocessor. All you will see is 0s or 1s. If you can see inside of that microprocessor in your cell phone, you couldn't tell the difference between a video, a picture, audio. It all looks the same. It's all represented or stored as 0s or 1s, machine language or binary. So it's kind of interesting to think about that. All right, so any questions or comments on the first question, figure 1-2 on Canvas if you have a handout? How are 0s or 1s represented inside of a digital device? Any questions over that? Okay, well, if there are no questions, let's move to the next topic here. I want to talk about pulses. Now, I can store, it's pretty easy to store a 1 or a 0. And you might say, well, what do you mean it's easy? Well, there's devices that actually hold a voltage. I can have I don't know if you guys, I think most of you guys had the circuits course. If you had the circuits course, and you might have talked about a device called a capacitor. Or you might at least have heard of a capacitor. Well, capacitor is a device, an electrical component that you can charge up. So if I want to charge, if I want to store a binary maybe code like 1101, the symbol for a capacitor is like this. And I can actually take a capacitor. So I take this capacitor, I hook it up to a 10-volt battery, I disconnect this, and now that capacitor is charged at 10 volts. So I can actually, and they used to do this, in the early days of computers, they would have these memories that had these little tiny microscopic capacitors in it. And so they might have 4 capacitors kind of lined up like this. If I want to represent the value 1101, what I would do is I would charge this first, well, I wouldn't, but the machine would charge this first capacitor up to 5 volts, the second capacitor to 5 volts, the third one to 0 volts, and then the last one to 5 volts. So I can actually have these capacitors store these voltages. They can do it could be done magnetically. There's a lot of ways to represent these binary values. The point is, though, is that when I represent this information, say I have a pixel, which is a piece of a picture or video, or I have a piece of audio information I want to digitize and put into a digital device. Well, I can represent that pixel or that piece of audio with zeros and ones, machine languages. On the physical level, it's these voltages, the presence or absence of a voltage. But what happens when I want to move that information around? What happens when you snap a picture? You snap a picture of something on your cell phone, and you want to send that picture to your friend, right? So you snap a picture, and all of those pixels taken in, converted, the analog information is converted to pixels and taken in. Each one of those pixels in the picture is represented by zeros and ones. So now we have it stored. Some kind of way, some place we have it stored, those zeros and ones stored in the device. But how do I move those zeros and ones from one place to another? Maybe from your cell phone to another cell phone, or if I'm dealing with a computer, I might have it to move information from the memory to the microprocessor. How do I move bits around is the question. And so that's what we get into when we talk about digital pulses and waveforms. So let me talk about what I mean by a digital pulse. I'm going to show you 2 types of pulses. So one looks like this. And this is the low value of voltage, and this is the high value of voltage. That's the high and that's the low. Now remember, in here, we're using 0 volts to represent a low. We're using 5 volts to represent a high. So then what I'm saying is right here, this would be 0 volts, and then that's 5 volts at the very top. Well, this part right here is we have a 0 volts, of course, for a certain amount of time we have 0 volts, and then this thing goes up to 5 volts. It stays at 5 volts for a certain amount of time, and then comes back down to 0 volts, and then it stays at 0 volts. So this first part right here on the left, this is called the rising edge. Rising edge. So this is the rising edge, and right here, this part right here, that's the falling edge. So that represents the falling edge. And this pulse is called a positive going pulse. This is a positive going pulse. If I wanted to, instead of starting at a low voltage, going up to a high voltage for a certain amount of time, and then dropping back off to a low, I could do it the other way if I wanted to. I could start off at a high voltage. Maybe I start off here. I drop off. I go to a low voltage. I stay at that low voltage for a certain amount of time, and I come back up to my high voltage. So now, here's my high. Here's my low down here, as far as the low. And this part now is my falling edge. And this right here is my rising edge of my waveform. So all I got to do to make a digital waveform is I deal with time here, T-I-M-E, time. I start off, if I want to make a positive going pulse, I start off at a low value, 0 volts. I stay at 0 for a certain amount of time, and then I go up to my high value, 5 volts. I stay at 5 volts for a certain amount of time, and I go back to 0 volts, and I'm at 0 for the rest of the time. This is called a positive going pulse. If I do it the other way, if I start off at 5 volts, I stay high or at 5 volts for a certain amount of time. I drop off to 0 volts. I stay at 0 volts for a certain amount of time, and I go back to my high value, and that is a negative going pulse. Negative going pulse. Now again, these are ideal pulses, and I say ideal because, well, really there's something wrong with this picture, isn't it? And what's wrong with it is right here at that point and that point right there. What's wrong with it is that we go from 0 volts to 5 volts and instantaneously in no time, and you know that's impossible. So while we in this class will think about our digital pulses like this is an ideal pulse. In reality, that's not what happens. In reality, it takes time to go from 0 to 5 volts or from 5 volts back to 0. It takes time to do that. So the actual ideal digital pulse really becomes this. I'll try to draw it as best I can. So my 0 volt point right here, this is my low, and this is my high. So this is my 0 volts right here. It takes time, actual time, to come up here to 5 volts. And so actually in any kind of digital device where you're moving around zeros and ones, you don't really have this, you have this. And this is kind of an issue because if you think about it, well, here's what they do with this. I don't want to go into too much details because we're not going to think about it this way. But what ends up being done here is at the bottom part of this is called the baseline. This is the base. And this height right here, that height right there is called the voltage amplitude. That's the amplitude. This height is the amplitude. And so for us, it's 5 volts. But what they'll do is they'll come down 10% from the max amplitude, and they'll take a point. They'll come down 10%. So now we're down to 90% point. And they'll go up 10% from this baseline. So they'll go up 10%. So we're at a height of 10% above the baseline. And they'll sample the values of voltage at 10% above the baseline and 10% below the max amplitude. And then right in between those, and the reason they do that is right here, instead of having the sharp corner right there, this part right here is nonlinear. Right at that corner is nonlinear. You don't have this nice sharp point there, and there. You have these nonlinear portions of this waveform. So this is nonlinear, this is nonlinear, this is nonlinear, and this is nonlinear. So what they do to get around that, if they go up 10% above the baseline and down 10% below the max amplitude, then this part right here is pretty much linear. So we're just dealing with part of that waveform. Then they go right smack dab in the middle of that, the 50% point, like right here. So that's the 50% point. And that 50% point right here, right in here, between those two 50% points, that's called your pulse width. So that's your pulse width. And that's represented, they use a T sub W for that. That T stands for time. So that's your pulse width. And so this is what we'll think about in this class, but in actual machine, it gets a lot more complicated when you look at what's actually going on in your cell phone or computer. This is actually what you deal with. And so they have this thing, and again, I don't want to get too detailed with this because for what we're going to do, you don't have to. But if you were electrical majors instead of mechanical, I think I got a couple METs and MEs, then we have to worry about how long does it take this waveform to go from 0 to max. There's a rise time and fall time of the signal, and it gets kind of detailed, but we won't worry about this. I won't ask anything about that. That diagram is just there for your information. You can look at that. We'll only deal with ideal pulses. But you do have to know the difference between a negative going pulse and a positive going pulse. So if I start off at a low voltage, go up to a high voltage for a certain amount of time, and come back down to a low, that's a positive going pulse. And if it's the other way, where I start off, let me go ahead and draw it. If I start off at 5 volts, drop to 0 volts for a certain amount of time, and then come back up to my high, and that's a negative going pulse. So that's pretty much the extent of what you got to know about digital pulses. Okay, so let's just kind of step back and look at what we've talked about so far. So most of the information that we're going to measure some physical quantity and get that into our digital device, we got to change it to digital. To do that, we have to take samples, and for each piece of the sample, we represent that sample with zeros and ones, a digital code. I can store that digital code in binary, and we know under the hood of the car, in the actual machine, a binary 1 is really the presence of some amplitude of voltage, in our case 5 volts, a binary 0, 0 volts. Well, we talked about that. Now what I want to do is, we want to move these ones and zeros around. Well, to do that, the first thing we got to understand is this idea of a pulse. So I have a positive going pulse, and I have a negative going pulse. Now what I can do is I can take more than one pulse and put it together. Let me do that. So I take more than one pulse and I put it together. So I got this pulse. I'm going to add another pulse to it. And then another pulse. Once I start adding pulses together, this is called a pulse train. A pulse train. And there's two kind of pulse trains I want to talk about. There's this one, and there's another one that looks like this. Both of those are pulse trains. Well, the difference is, if you think about it, and I don't know, my artwork is probably not that good, but what I was trying to do is draw this kind of symmetrical, and each one of these are exactly like the one before it. Whereas this one, I got a long time where I'm at 0 volts, and I got this time where I'm at high voltage 5 volts, and then so this one repeats itself in regular intervals, and this one it doesn't repeat itself. When a pulse train, or I like to use the term waveform, so waveform, and it's actually a digital waveform, but I don't use the word digital. When I say waveform, I'm implying it's a digital waveform. So this waveform or pulse train can be either periodic or non-periodic. This is an example of a periodic waveform because it repeats itself at regular intervals. And this is an example of a non-periodic waveform because it doesn't repeat itself. So the first thing to understand about waveforms, and again, we're talking about waveforms because this is going to help us to move ones and zeros around inside of our devices or outside of our devices. If I have a waveform that repeats itself at regular intervals, we call that a periodic waveform. If it does not repeat, non-periodic. So this one right here is periodic. And this is non-periodic. Now it turns out what we do is we use periodic waveforms in digital devices for timing purposes. So this right here is for timing. And then we use this to represent actual data. So we use periodic waveforms to represent timing, and we use non-periodic waveforms to represent the actual data, the zeros and ones we want to move around. Now, I want to focus on periodic waveforms for just a second. When I have a periodic waveform, there are two concepts that apply only to periodic waveforms. It doesn't apply to non-periodic waveforms. One concept is this idea of period, and the other is called frequency. So the concept of period and frequency. Most people have heard of frequency. You might not know really what it is, but you've heard of frequency. I don't know if you heard of period or not, but let's give definitions of these. Well, the period of a digital waveform, the period, is how much time it takes for the waveform, one cycle of the waveform, to repeat itself. How much time does it take? So for example, if I start right here at this corner, I don't know if let me see. I don't know if this red shows up in the camera. Hopefully it shows up. Let's say I start right here. That's my starting point. I come up to a high value. I stay at a high value for a certain amount of time. I go to a low value. And then right at this point, it starts to repeat. The part that repeats is this. It's up, down, over. The part that's repeating is this. Up, stay high for a while, come back down. And at that point, the second cycle starts. I'm going to draw the second cycle in a different color. The second cycle is that. And then the next cycle is that. So one of these right here is the thing that repeats. And so the period is the time that it takes for one of these. It's the time. So what we usually do for period, what I do is I represent period like this. A T with the two sides on it. So that represents the time for one cycle. The frequency, on the other hand, is how many of those pulses you see go by in a second. So some of you, you've probably seen frequency, the idea of frequency. Well, you know the wall outlet in your house, the electricity that comes out of the wall, the AC is 60 hertz. It's 60 cycles per second. Now, in that kind of electrical situation, we're not dealing with square waves, we're dealing with sine waves, but the idea of frequency and period is still the same. If I have 60 cycles per second, or 60 hertz, that means I have 60 of those things that repeat go by a certain point in a second. So the frequency is how many things happen inside of a time space of 1 second. There's a relationship between period and frequency, and it's pretty simple. The relationship is that the period is equal to 1 over the frequency. The period is equal to 1 over the frequency. Now, I mentioned to you that we use these periodic waveforms for timing purposes. Now, let me explain to you why it's important. Let's say I had this. Let's say I had, let me get rid of this. I don't know if, I'm gonna try to write it down here. Hopefully you can see it. Let's say I have some bits that I want to move around. So I want to move around bits, and I can actually represent a. Well, I guess I just have to erase this. I can actually represent with this pulse. I can use that to represent a binary 1. I can use a positive going pulse to represent a binary 1. I can use a negative going pulse to represent a binary 0. And so if I have, say, a code, maybe 1100, I can actually move that code from one part of a computer or digital device to another part, or from the inside of the digital device to the outside, maybe from one cell phone to another, using these digital pulses. The problem is, what if I gave you something like this? What if I gave you a digital pulse that looks like this? The problem with this is, if this represents data, digital data, 1s and 0s, is I got one really long positive going pulse here. I got a little short negative going pulse here, and then another positive going pulse here that I kind of cut off on the side. I don't know. I know this can represent a 1 or a series of 1s, but I don't know how many. I mean, is this one big 1, or do I have several 1s here? How many zeros does that represent? How many 1s does this represent? There's no way of telling by just looking at this. This is the non-periodic waveform, the non-periodic. And so here's what we do when we deal with these digital devices, and I want to move bits around. Every digital device, your cell phone, computer, refrigerator that's programmable, anything that has a microprocessor, inside of that microprocessor is a tiny circuit called a clock. I usually spell clock like this. And all that clock does is put out a periodic waveform. It puts out one of these. Your cell phone has a clock. Your computer, any digital device has circuitry that we call a clock circuit. When you buy a computer, if you ever bought a computer, a laptop, I don't know what the microprocessor speeds are. Maybe you might buy a computer and it's like, I don't know what they are now, maybe what, 5 gigahertz? They say you have a clock speed of 5 gigahertz. What does that mean if your computer's, you know it's fast, but what does it mean? What they mean is the clock speed of the computer. The waveforms that clock puts out 10 gigahertz, and that's pretty daggone fast. So you talk about frequency of a computer, you talk about the frequency of the clock, and the waveform the clock puts out looks exactly like this. It's always periodic. All right, so what you can do is this. Now, the question I'm trying to answer is, how many 1s does this represent? How do I determine if this is one single 1 I'm sending, or if this is a series of 1s I'm sending with this digital pulse? How many zeros is this? How do I determine that? Well, every digital device has a clock, and you use that clock to determine what we call the bit time. So let me write that down. I want you to write it down because on your, not the quiz that you'll have over the weekend, that's easy. You just watch a video, give me some answers, you'll get an A on that. But next Friday, I'm going to ask about this kind of stuff. You'll have to do some calculations. One of the things you got to understand is the bit time. The bit time. So let me write that down. Bit time. So the bit time is the time for one bit but more importantly, the bit time is always equal to the period of the clock. The bit time is always equal to the period of the clock. So bit time is found by finding the period of the clock circuit. And once you find the period of the clock circuit, then you can use that to determine how many bits you're sending. So let me show you an example of that. And actually I have one. I don't know if you have this diagram out. This is the one I actually take out. This is example, at the bottom there's like a figure 112. At the top you have a timing diagram like this. And then at the bottom you have a picture of a computer and a printer. Get this out, guys. Look at this. If you got that out, let's talk about this. They do a good job here. If you look at this, you kind of see what's going on. Figure 112, if you have that available. If you don't worry about it. I think it'll be clear when I do this, if I don't run out of time. But what they show you at the very top here, figure 112, they have a diagram similar to this, and at the very top is the clock. So you see the periodic waveform, and then they have these lines that break up. And remember, the period of that clock gives me the bit time. So between these two red vertical lines is 1 bit time. This is 2 bit times, 3 bit times, and so forth. So that's what they're showing on this diagram. And so on the diagram, it's a little more complicated than what I have here. But on this diagram, there are 3 data waveforms. The waveforms at the bottom, there's waveform A, waveform B, and C. That's the actual data. So when you move data around, you always have a clock signal. You have the clock, and then you have the data. So we got data, I think data A on that diagram, data B, and data C. We got those three data signals. And then you can see how they use the period of the clock to define the bit time. So right there at waveform A, that positive going pulse to the left represents a bit, one binary one. And then the binary 0 and so forth. So have a look at that. And again, if you don't follow what I'm saying, it's okay. I'll explain it here in just a second. But this is a good diagram to look at. At the very bottom of this diagram, in the middle, they show a computer on the left side and a printer on the right side. And what they're showing is they're transferring information. When you hit the print button on your computer, you're transferring zeros and ones from the computer to the printer. And the point here is you're transferring it bit by bit. That's called serial data transfer. If you transfer it bit by bit, like in a single file, you're transferring those zeros and ones in series, or you can do it like at the very bottom, the one at the very bottom, figure 1-13. That figure, you got looks like two microprocessors, or maybe microprocessor memory chips talking to each other. Typically, that's done in parallel. So sending bits in single file, you can send them all together in the group. So you got serial data transfer and parallel data transfer. And we'll get into the nitty gritty of that in just a second. But let me go back to this. So if I want to figure out, given this is my data right here. So this is data. This is my clock. That's my clock. And this is my data. Now I'm just showing one waveform, but you're going to have a lot of waveforms like on the sheet that I just referred to. Now, let's actually do a calculation. I think this will make more sense if we do a calculation. So guys, go to the handout. There's a practice problem that I asked you to print out. And at the top of it is a waveform, basically this waveform, which is figure 114. So that's on Canvas. And if you don't have it, don't worry about it. It's right here. This is the picture that's on here. I'll read the problem for you. But what you have here is you have a waveform. You have a clock, and you have data that we want to move around either between two digital devices or maybe between things inside of a digital device. You want to move them around. So the question is, what series of zeros and ones does this data represent? How would you determine that? Now let me read the question I want you to do. Get your calculator out if you need a calculator, and I want you to do the calculation. Part A says, determine the total time required to transfer the 8 bits contained in the serial waveform A. So this is A. This is A. This is the data. That's the waveform A. That's the clock. So the problem statement says, determine the total time required to transfer the 8 bits contained in the serial waveform A of figure 114 and indicate the sequence of bits. It says the leftmost bit is the first to be transferred, and the frequency of the clock is 100 kilohertz. The clock is always used as a reference. So what we know is the frequency of the clock, this periodic waveform, we know that frequency is 100 kilohertz. And what they want to know is, given the data, the purple, waveform A, what are the bits transferred, and what does that series of bits look like? So how would you figure something out like that? See if you can figure out. What you got to do is figure out, given the frequency, you got to figure out the bit time of the clock that defines the bit time, and you use that bit time to determine the bits that's being transferred in the data waveform. So take out your calculator. I'll give you just a minute because I only got like 6 minutes left. And I don't know. Yeah, I think we'll get through it today. I might go over a little bit, but we should get through everything today. So go ahead and get your calculator out. We're trying to figure out the ones and zeros in this data waveform. What does that look like? So what would you do first? Given the clock frequency is 100 kilohertz. The first thing you got to do is figure out your bit time. And then, if this were on a test, like in a quiz or exam, I would give you the frequency. You would draw the clock signal. You'd have the data signal. And you have to use that clock waveform to determine the series of zeros and ones. So let me pause for just about a few seconds, give you a chance to think about how you might do that, and then we'll work it together. The guys, don't just sit there. Just actually work along with me, even if you're a little bit confused. Because if you just sit there and watch this, then you'll get confused later on. It's kind of hard to teach through this camera. I can't see your faces. I don't know if you're getting it or not. So the very first thing you would do is to answer the question. And again, the question is, determine the total time required. How long does it take to transfer these 8 bits? How long does it take? Now I'm going to number these pulses so we can refer to them. Here's pulse number 1, 2, 3, 4, 5, 6, 7, 8. So I got 8 pulses from the clock. But remember, the bit time is not defined by the pulse width. The bit time is from the start of one pulse all the way over to the start of the next pulse. So the bit time, or the period, is that. So the first thing you do is figure out the bit time. Remember, I said the bit time is equal to the frequency. So go ahead and calculate the bit time. So the bit time is equal to the period of the clock, and that period is equal to 1 over the frequency. That's the equation I gave you for period, 1 over the frequency. And on a problem like this, you'll always know the frequency of the clock, or you'll be able to find the frequency of the clock. So if I find the period here, my period is 1 over the frequency. The frequency is 100, that's kilohertz. That's 10 to the 3rd hertz. I'll do my math there. I'll get 0.01, and that's kilo, so this would be milliseconds. So the period of the clock is 0.01 milliseconds. Let's change that to microseconds. That would be 10 microseconds. So the time from this point to that point, that bit time defines the time for 1 bit. And that time is 10 microseconds. So what I'm saying is that now, and I put these lines on there so I can draw it straightly, but all you will be given on the quiz, is the clock. You're given the clock signal, and then maybe you're given the data, like this. You would have to put those lines in there. You start here on the leading edge, you would divide it up, and then you would go through these calculations to find the bit time. You'd end up with a diagram like this. And I recommend that you number these pulses. You can see here the clock clicks 8 times. There's 8 pulses here. But the point I'm trying to make is this bit time defines 1 bit, and this bit time defines 1 bit. So I know that this is a binary 1, and this is a binary 1. This is a binary 0. This is a binary 1, 0, 1, 0, 0. That's how you determine, given something like this, if this pulse represents a single 1 or several 1 in series, you got to know the bit time. So instead of this representing 1 use 1, because of my bit time, I know that positive 1 pulse in the data waveform represents 2 ones. Okay? So we haven't answered the question yet, though, because what they want to know is, it says determine the total time required to transfer 8 bits. I got 8 bits, 1, 2, 3, 4, 5, I got 8 bits. What's the total time to transfer the 8 bits contained in waveform A if I'm going to transfer them in serial. That means bit by bit by bit. And to do that, if I use what we call serial data transfer, usually when you have a computer talking to a printer, those zeros and ones are transferred from your computer to the printer in serial, bit by bit by bit. And that's a slow process, relatively speaking. So if I have a bit time of 10 microseconds, and I have 8 bits that I want to transfer, that's going to take 80 microseconds to transfer those 8 bits. And you might think, well, that's pretty daggone fast. But remember, in a Word document or a picture video, you might have billions, if not trillions of bits that you have to move back and forth. So actually transferring bits, moving bits around in serial is a pretty inefficient process. It's pretty slow. But the advantage is it's really simple. If you look at this diagram, again, I'm referring to figure 112, that timing diagram. In the very middle, they have a computer and a printer, and there's just line going from the computer to the printer. So the advantage of serial data transfer is as simple. The disadvantage of moving bits in serial fashion is that it's slow. So that's part A. Part A, determine the total time required to transfer the 8 bits contained in the serial waveform A of figure 114. Well, the total bit time was 80 microseconds. And it says indicate the sequence of the bits. So it looks like that this bit is going out first, that 0, but that's not what they tell you here. It says the leftmost bit is the first to be transferred. Now that's important that you understand that. This is a timing diagram, and if I made a graph, and I'm out of time, guys, if you got to sign off, go ahead. I'm going to go ahead and finish, and if you guys have to sign off, just go back and you can watch the video towards the very end. I'm almost done here. I don't want to stop. So let me just show you this real fast. Even though it looks like this is the first bit to move over to the right, and this one, if make a graph out of this. Think about it in terms of a graph. If you have a graph, and here I have my time, and this is my amplitude. If I lay this waveform down on this graph, it looks like this. It looks kind of like this. I won't draw the whole thing, but the point is this part right here, and time happens before this part right here, because the seconds go up as I move further and further to the right. So even though it looks like if these bits are moving to the right, it looks like there's a 0 transfer, then there's another 0 transfer, then there's a 1 transfer. In reality, in time, you see this 1 first. The first bit to go is that 1. We transfer a 1, then we transfer the other 1, then we transfer a 0, then we transfer a 1, and so forth. So they asked, and I don't know if I would ask this on the quiz or not, they want the sequence of bits. Here's my sequence of bits. It's not 0, 0, 1 first. It's 1 first, and the 1 first, and so forth. I think you get what I'm saying. And then very quickly, part B, it says, what's the total time to transfer those same bits, 8 bits, in parallel? Well, in this diagram, at the very bottom, they show a microprocessor talking to memory, or maybe memory talking to a microprocessor. And typically, inside of your cell phone or computer, when those devices inside are communicating between each other, they do so in a parallel fashion. When you transfer information outside, like from a digital device to a printer, typically they do that in a serial fashion. And the reason is, serial is way less expensive, but it's slow. A printer can afford to wait. It can afford to be slow. But inside your device, inside memory, it's got to be super fast. So the difference is, and I'm going to quickly draw that diagram. What they have on that diagram is they have a device here. So maybe this is your microprocessor, micro P. And over here, this digital device, maybe that's memory. And I have these binary digits in here. Maybe I got I got that. I got a 1, 1, 0, 1, 0, 1, 0, 0. And I want to move it from a microprocessor to memory. Well, what I showed you in this diagram was I got the computer here, and I got the printer over here. I got one line, so these bits are set bit by bit by bit, and that took 80 microseconds. Well, if I inside of your device, I actually have these lines connected. There's 8 of them. There's a line like this, like this. There's 8 lines in here. 8 of them. There's a line for each bit. So instead of transferring bits in single file from microprocessor to memory, one click of the clock, all these bits are transferred over here in one clock pulse, 1 bit time. So in parallel, I can move the bits all in one group together. And so for this example, at the very bottom it says, part B, it says, what will be the total time to transfer the bits if I transfer them in parallel? The answer would be, it would take 1 click of the clock, and remember that was 10 microseconds. It took 80 microseconds to move them bit by bit, serial data transfer. It only takes 10 microseconds for parallel data transfer. The disadvantage though is, this is much faster, but you can see it's way more complicated. It requires more lines. Okay, so I'm way past my time here. I got one more thing I want to talk about, but I want to pause here to see if you guys have any questions. And I'm going to finish out this recording. I just want to talk about something called the shift register, and I think I'm pretty much done. And if you have to sign off, then go right ahead and sign off, and just please, when I post this video, go back and watch the end of this. I just want to talk about one more topic. Let me pause. Anybody have any questions? I went through this kind of quickly, but hopefully it was clear. Any questions or anything I talked about so far? Okay, well let me close out by one more quick topic. There's a diagram. I didn't tell you to print this out, but you'll see it. It says example operation of a 4-bit serial in shift register. So what is this? So I want to talk about something called a shift register. Remember earlier in our discussion when I said that you can store ones and zeros by charging up a capacitor? So I had like 1, 1, 0, 1, and I said I can take a capacitor and charge this one up, charge that one up. I don't charge this one. I charge this one up. So this capacitor right here is charged up to 5 volts. This capacitor, 5 volts, 0 volts, and 5 volts. So inside of the computer or cell phone, what's actually stored when I'm talking about a 1 is a 5 volts, was actually stored. I'm talking about a 0 volts. Well, there's another way to store these zeros and ones, and it's called a shift register or register. And a register is an actual component that you can go to the store and buy. You can go to the electrical store, electronics store, and you can buy a 8-bit shift register, or you can buy a 16-bit shift register. So if you knew circuits, you can go and you can take that shift register and put it in a circuit, and you use it to store ones and zeros. A shift register is just an actual circuit or device that you use to store bits. And the way to think about it is like this, just boxes. So a 4-bit shift register is just a container, and it has these 4 spaces that I can put bits in. So I can put ones and zeros in here. Might put something like this in there. The question is, how do you get those bits into and out of the shift register? You go buy this device, and at first it's empty. Let me redraw this. At first it's empty. So I go get a shift register. And I got this code. I want to put that digital code into my shift register. Well, one way to do it is to have one line in the register like this, one wire going in and one wire coming out. So if I have this is called a serial in, serial out shift register. And what happens is that every time the clock clicks one time, and this bit right here will, let me make this a different color. On one of the clock pulses, this will move over into here. And then on the next clock pulse, the 0 will move over, and that 1 will move in. And then on the next clock pulse, the 0 will move over here, the 1 will move over here, and another 1 will move in there. And all I got out here is that 0. And you see what's going to happen? It's going to take 4 clock pulses, and then at the very end, I'll end up with, in that shift register, this 0, 1, 1, 0 inside of my shift register. And that's what this diagram shows. If you get a chance to look at this, it shows this example of a serial in shift register, and it's showing you the number 0, 1, 0, 1, and how many clicks of the clock it takes to load that register. It's going to take 8 clicks of the clock, 8 pulses. If you know the bit time, you can determine how much time it's going to take to load that register. What you got to know is this. If I have, I'm just going to draw a box. If I have a shift register like this, with one line in and one line out, this is called serial in, serial out. If I wanted to, I can have a shift register like this, where I have one line in, but then I got 8 or 4 lines out like this. So if I wanted to load that 0, 1, 1, 0, it's going to take 8 clicks of the clock, 8 pulses to load that. So I can load it, and I'll have this 0, 1, 1, 0. When I want to read it, get those zeros and ones out, they're all available at one time. So this is serial in, parallel out. It takes a long time to read the information and to write the information to the shift register, but you can get it out real quickly. So if I show you a diagram like this, this is serial in, serial out, serial in, parallel out, and then finally, I can have something like this. Maybe I have a 4-bit shift register. I got 4 lines coming in, and I got 4 lines coming out. And if I want to put that number in, 0, 1, 1, 0, it only takes 1 click of the clock, and all these bits drop down into here. It takes 1 click of the clock, and I can read the bits down here. They come out at 1 click of the clock. So parallel in, parallel out is the fastest, but it's also the most complicated. So given a diagram like this, all you got to do is look at the direction of the arrows, right? Serial in, parallel out, parallel in, parallel out, serial in, serial out, that kind of thing. So guys, sorry I went way over. I apologize. I do have a couple other diagrams I want to refer to. I'll probably close that out on Wednesday. Anybody have any questions for me before I sign off? Okay. If you do, you can always text me. Have a safe and weekend. Enjoy your weekend. I'll see you guys on Wednesday. If anything comes up between now and then, just send me a text. And please remember, I'm going to send you a link to a video on relays. I want you to watch that video, and then when you go take the quiz, you'll have the whole weekend to take it. But once you start it, it's time. Then it's just going to ask you some basic questions about the video. Okay? So guys, have a great weekend. I will see you later.